In this unit, we will study about Laplace transforms and Z transforms. First, we'll start with Laplace transform. So there are two definitions for Laplace transform. The first one is the bilateral Laplace transform, and the next one is unilateral Laplace transform. So bilateral Laplace transform is defined as f of s equals to integral minus infinite to plus infinite f of t e power minus st dt, right? It is called bilateral because it is defined for both positive as well as negative values of t, right? If your f of t, right, it is defined for both negative as well as positive, it is generally considered as bilateral Laplace transform. Similarly, unilateral Laplace transform is only defined for positive values of t. So we'll integrate only from 0 to infinity f of t e power minus st dt. Here s is the Laplace transform variable, right? S is the Laplace transform variable, similar to omega for Fourier transform, and capital omega for DTFT, capital omega for DTFT. S is for Laplace transform, and S is a complex variable, so I can write it as in real form sigma plus j omega. S is a complex variable. In real form, I'll write it as sigma plus j omega. So this is definition for Laplace transform. Laplace transform of any given function f of t is equals to f of s. S is the Laplace transform variable, and it is defined as integral minus infinite to plus infinite f of t e power minus st dt, where s is sigma plus j omega. If it is defined for both positive and negative values of t, then we call it bilateral Laplace transform. If it is defined only from 0 to infinity, then it is called unilateral Laplace transform. Now, similar to other transform pairs, Fourier transform pair and DTFT pairs, we'll write the Laplace transform pair. Now, Laplace transform pair is f of t has Laplace transform capital F of s, capital F of s. Now, if I have g of t, its corresponding Laplace transform is going to be capital G of s, capital G of s. So this is about the definition for Laplace transform. Next, we'll look at the condition for existence of Laplace transform. What was the condition of existence for Fourier transform? We had three different conditions. The first is absolute integrability. The second one is maxima and minima. There must be finite number of maxima and minima, and there must be finite number of discontinuities. In case of Laplace transform, there's only one condition. That is integral minus infinite to plus infinite mod of f of t e power minus sigma t dt must be less than infinity. It must be some finite value of sigma, for some value of sigma, right? If you assume some finite value for sigma, then integral mod of f of t e power minus sigma t dt must be less than infinity. This is the condition for existence of Laplace transform. So for the Laplace transform to exist, this above integral here, it has to converge. That is, it has to be some finite value. Then advantage of Laplace transforms. Signals which are not convergent in Fourier transforms are convergent in Laplace transforms. For some signals we cannot find the Fourier transform, right? For example, e power 3t u of t. I can't find a Fourier transform for this signal because if I integrate it from minus infinite to plus infinite, this will not converge. It is going to be infinity. It is going to be infinity if I integrate it, right? So for such signals, I can find the Laplace transform. I can find the Laplace transform. How? What is the condition for the existence of Laplace transform? Minus infinite to infinite. My signal f of t, right? F of t into u of t. This is my signal, and I have to multiply it with e power minus sigma t, the entire thing mod dt must be less than infinite, right? This is the condition for existence. Now I will eliminate this u of t here. If I eliminate u of t here, what will happen? My lower limit will now become 0, right? Because u of t is defined only for 0 to infinity. Now this entire thing inside my modulus, what is it going to be? It is going to be e power, what can I write? E power minus of sigma plus 3t, right? If I integrate it, I'll get e power minus, let me say this is some x. So e power minus xt divided by minus x, right? And then the limits are 0 to infinity. Now if I substitute infinity in place of t, what will I get? E power minus infinity, that is 0, minus, if I substitute 0, I'll get 1 by minus of x, right? 1 by minus x, that is 1 by x. Now what is x? X is sigma plus 3. When sigma is a finite value, this term is also finite. So I can say my Laplace transform exists for my f of t, which is e power 3t into u of t. But for the same function, I cannot find Fourier transform. That is the advantage of Laplace transform. For signals which are not convergent in Fourier transform, I can find the Laplace transform. Then the next advantage is differential equations of a system can be converted into simple algebraic equations. So analysis of LTI systems becomes easy. So analysis of LTI systems is easier in Laplace transform. That is the second advantage in Laplace transform. Now we have advantages. We'll also have disadvantages. What is a disadvantage? Frequency response cannot be calculated. Frequency response cannot be calculated using Laplace transform. Using Fourier transform, I was able to calculate frequency response, right? I was able to calculate f of omega. From that, I was able to calculate my mod of f of omega as well as angle of f of omega. I was able to calculate the magnitude and phase spectrum using Fourier transform, right? But using Laplace transform, I cannot calculate the magnitude and frequency spectrum. These two I cannot calculate using Laplace transform. So then what can we find using Laplace transform? By using Laplace transform, I can say directly by looking at the Laplace transform for which values of yes my Laplace transform is existing. By looking at that, I can say if my system is stable or not, directly by looking at the graph, right? This is the S graph. We'll look at this later, but for now, that is what we'll do using Laplace transform. Stability of the system we can analyze using Laplace transform. This S equals to j omega is used only for sinusoidal steady state analysis. This is other limitation of Laplace transform. Then So now we have been comparing Laplace transform with Fourier transform. So let us find the relation between the two transforms. How is Laplace transform related to Fourier transform? So let us first assume Laplace transform. Laplace transform. What is the function definition of Laplace transform? It is f of s equals to integral minus infinite to plus infinite f of t e power minus st dt. Now, in place of s, I'm going to substitute, since s is a complex variable, I'm going to substitute sigma plus j omega. Right? Now, I will separate these two exponentials into this exponential into two exponentials, that is e power minus sigma t multiplied with e power minus j omega t. Now if I combine these two, and I call it some x of t, let me just call it x of t now. So what is this in the form of? Integral minus infinite to infinite x of t e power minus j omega t dt. What is that? That is nothing but Fourier transform of x of t, right? That is nothing but Fourier transform of x of t. Now what is x of t? F of t into e power minus sigma t. F of t into e power minus sigma t. So this entire integral is going to be Fourier transform of f of t into e power minus sigma t. Right? So this is the relation between Laplace transform and Fourier transform. Laplace transform of f of t is nothing but Fourier transform of f of t into e power minus sigma t. Now, when I substitute in place of s is nothing but sigma plus j omega. If I make sigma equals to 0, if I substitute sigma equals to 0, s will be equals to j omega. Now, what will happen? If I make sigma 0 in this integral, e power minus 0 is going to be 1. So what is this entire thing going to reduce into? Integral minus infinite to infinite f of t e power minus j omega t dt. That is nothing but Fourier transform of f of t. Right? It is nothing but Fourier transform of f of t or f of omega. So now what can we say? Fourier transform of f of t, in this case I'm calling it continuous time Fourier transform just to differentiate it from dtft. So Fourier transform of f of t is nothing but f of s when s equals to j omega, right? F of s, in place of s, if I substitute j omega, that is nothing but my Fourier transform. If I take the Laplace transform f of s, and if I substitute s equals to j omega, I'll arrive at my Fourier transform, right? This is the relation between Laplace transform and Fourier transform. So Laplace transform at s equals to j omega is nothing but Fourier transform, right? This is an important relation between Laplace transform and Fourier transform. Now we have been saying that s is the Laplace transform variable. So we'll look at the s plane. Previously we were looking at omega as the Fourier transform variable. So we had omega, that is the complex omega plane. Now we are going to look at complex frequency plane, that is s plane, in case of Laplace transform. This is the complex frequency. S is the complex frequency and it is written as sigma plus j omega, right? Real part sigma and imaginary part omega. Now in S plane, this real part is shown on the x-axis and imaginary part is shown on the y-axis, right? Real part is shown on the x-axis here and the imaginary part is shown on the y-axis. Now, this real part of S will range from minus infinite to infinite. Similarly, the imaginary part will also range from minus infinite to plus infinite. Okay, and then this S plane is used to represent critical frequencies. We call this critical frequencies, that is nothing but poles and zeros, which are used in designing systems with desired response. We'll look at what are poles and zeros later. So these poles and zeros are represented using the S plane. I will represent the poles and zeros of my given system or signal using the S plane. So we'll look at what are the poles and zeros later, or let me just introduce poles and zeros. Suppose I give a Laplace transform h of s. I have a Laplace transform h of s. H of s is equals to s divided by, let me say, s plus 1 and s plus 2, right? Now I have to find the poles and zeros of this particular system with the transfer function h of s. Now what is a zero? Zero, 0 is nothing but roots of my numerator. Zeros are nothing but roots of roots of numerator, right? So if I make the numerator 0, what will I get? S equals to 0. So this is my 0, 0 of zeros of my system. Similarly, if I make my denominator 0, I will get my poles. Poles are nothing but roots of denominator. So if I make my denominator 0, what does it say? S plus 1 will be equal to 0, or s plus 2 equals to 0. So my poles will be s equals to -1 and s equals to -2, right? So I will represent my zeros and poles in my S plane. How? Zeros are represented by a circle. Zeros are represented by a circle, and poles are represented by a X mark or a cross mark in my S plane. So at S equals to 0, I have a 0. 0 means I can write it as 0 plus J 0, right? Real part is 0 and imaginary part is 0. That is somewhere here. So I will denote a 0 here. This must be a circle, okay? Then poles. Poles at S equals to -1. The real part is -1 and imaginary part is 0. So at minus 1, I have a pole, and at -2 also I have a pole. So this is how I represent my poles and zeros in the S plane.